I have everyone's attention, please? The next talk is about to start. All right, so if you have the booklet, the first question is there, if driverless vehicles are ripe for the hacking, and that is why ZoZ is here today. ZoZ is a robotics interface designer and a rapid prototyping specialist, and he is going to present hacking driverless vehicles.
All right. Thank you. It is great to be back at BruCON again, and it's really exciting to have a chance to give this as a retro talk, because I really was wanting to update this talk anyway, because some really interesting stuff had come out since I gave it at BruCON 6, if I recall correctly. So I sort of took the instructions to heart here about presenting pretty much the original talk, and then plus some sort of updated stuff. And then I was, I was sort of on the fence about it today, and thinking like, maybe I shouldn't have like included all of the old stuff, like basically every single slide from the original one. And then I saw this morning the number of people that stood up saying that this was their first BruCON. So then I felt a lot better about basically doing the original one. But because I added a bunch of stuff to it and a live demo, I thought that I'm going to have to go real fast through some of the intro stuff. So bear with me on going through a lot of that stuff fast, which I'll start off going fast with my intro stuff. Most people know me, well, more people know me than from anything else for the TV show that I did called Prototype This, in which we did a few unmanned systems. So we did an autonomous drone aircraft that delivered life jackets to people who were in trouble in the water, and we crashed a lot of aircraft, so we learned about failures in the air. And we also did ground-based autonomous vehicles for delivering pizza. So we did a small two-wheeled self-balancing pizza delivery vehicle for local delivery, and we did a full-size vehicle for delivering pizza over large distances. And as part of this project, we did the first ever autonomous crossing of a United States highway bridge. So real driverless vehicles. I also host autonomous robotics competitions for RoboNation, so you can check out those. Many of them are maritime competitions, boats and submarines. So originally when I put this talk together, the motivation was to not to say like, oh, we're gonna mess with driverless vehicles and they're going to be a total disaster. The motivation was that these things are coming. We're going to be riding in autonomous vehicles before too long, and so we need to sort of understand what the vulnerabilities are. And the reason why we know that we're going to have autonomous systems around us is because of the many advantages that they hold. So the energy efficiency of not having to carry human pilots, the time efficiency of being able to go places without having to stop to let the human driver go to the bathroom or sleep or whatever, and all the things that we can do that with autonomous vehicles that we couldn't do if we had to have a human on board. So we're not going to be stopping the revolution by threatening to hack driverless vehicles, but the system's going to be created, they are going to be hacked, so we need to start talking about their vulnerabilities before they're so entrenched that they're a total disaster. IoT. So here's a slide that I put up originally at BruCON talking about European driverless vehicle efforts. And I thought it would be interesting to sort of contrast what I said a few years ago with how things have actually turned out. So the UK said that they were going to start on-road testing starting in 2015, and they were going to put £10 million towards a research fund. Sweden promised a fleet of 100 driverless Volvos in Gothenburg starting in 2017, and that was sort of how it was 4 years ago. Let's have a look at how things turned out. So in the UK, Nissan has been testing autonomous Leafs in London since 2017. Jaguar Land Rover has been testing on public roads. That £10 million is now up to £200 million in the research fund. In Sweden, they did start driving driverless Volvos in Gothenburg in 2017. They just made it, December 2017, and it's going through this year. And they have an autonomous bus that was approved in Stockholm this year. In Germany, they have 40 BMWs being tested in Munich, and they have promised an autonomous electric vehicle that will drive on the Autobahn in 2021. Autonomous buses are all the rage in Europe. So they've got one going in trials in Berlin, also in Bavaria. France has automated shuttle buses. Buses are a great place to start with driverless vehicles because they don't move too fast and they stop all the time. So the downside risks of getting in accidents and stuff are lower than driving at highway speeds. France is getting their legislative act together to allow open road testing. And there's this project Autopilot from the EU, 6 cities, 25 million euros. And right here in Belgium, there was a self-driving delivery van test in 2018. And again, low speeds, maximum speed 8 kilometers an hour. And I think I saw an autonomous shuttle vehicle here in Ghent yesterday. I didn't get close enough to get a good look at it, but it was cruising very slowly down the tramway. So, you know, the predictions from 4 years ago, yeah, mostly have come true. So I'm definitely not here to spread fear, uncertainty, and doubt about robot vehicles, right? Not alarmist anti-robot propaganda that I'm trying to do. So what I'm trying to say is that these vehicles are so good at what they do. Here's a video that I shot of an unmanned helicopter system. They're so good at what they do that we're going to see this uptake very quickly. Helicopters are notoriously difficult to fly. A moment of inattention and you'll crash. And robots are just really good at not doing momentary inattention and keeping everything under control tightly. But while I was filming this video, this is the Fire Scout helicopter. When I was filming this, I noticed on the wider angle where the people who were controlling, you know, who had the laptop and was setting off this flight they were hiding behind the start cart just in case something went wrong. And so that's the security mentality, right? Just to think about the robustness of the system. And in fact, this airframe did subsequently crash. You can see it. It's on display in a museum in Oregon, in the Evergreen Aviation Museum. It crashed, and they gave it away, and they put it back together in the museum. So, you know, we have to think about the failures, the possible failures. So this was just some stuff that I originally did just to sort of define the space of autonomous and unmanned systems so that we can have human passengers, but just not a human driver. We can have an off-board pilot, that kind of stuff. But I'm just going to sort of go through this stuff quickly because I have new material to get through. Here's a slide with a graph from 2011 showing uptake of one particular unmanned aerial platform in the US military. So that's the sort of like, yeah, the exponential uptake is happening. On the other hand, you have this quote from Congress who in 2001 said they wanted 1/3 of the operational US military ground vehicles to be unmanned by 2015. And so at present, we have approximately 0% of the operational military ground vehicles being unmanned. So some things aren't going as fast as people thought they were. Here's another vehicle that I took a photo of. That's, again, an unmanned ground vehicle, but has been designed with threats in mind because the military designs for threats. So it's got all kinds of armaments and various kinds of sensors and so on. But again, it's in testing. There's all kinds of kill switches all over it as well. So all you have to do is get close enough to press the big red button, and you're just fine. And then I had a quick overview slide of the kinds of applications that we're talking about where you might see these things crop up in the civilian space. Forget about the military. They have obvious threat models. They have obvious applications. But in the civilian application, of course, we've got our driverless transportation. Maritime applications like oceanography, super important because it's just not cost effective to send out giant ships full of people to do oceanographic research. It's super, super expensive. It's dangerous. You can't operate in particularly bad weather, but the robot can just go out there and be out there for a long time. And if you lose it, it doesn't really matter. Mapping, of course. Filmmaking, now you can spend under $1,000 and get an awesome aerial filming platform that previously would have cost tens of thousands of dollars per flight to have a real helicopter. Things you wouldn't think of necessarily, like power line inspection. There's millions of miles of power lines, and someone needs to go out there and inspect them and see when they're going to corrode and break. And then autonomous delivery and logistics. A big one here in the maritime space is unmanned cargo shipping. So, and a big reason for that is maritime accidents are mostly happen because the humans screw up in some way. They're drunk or asleep or whatever, make the wrong decision. On the other hand, these voyages are long and things go wrong. And so most of the reason why you even have a human crew now is to fix things when they go wrong. And that's something that still has to be dealt with when we talk about robotic vehicles. What about when just things normally break? The priorities for civil applications, precision agriculture, and self-driving cars. That's where the industry lobby group that supports unmanned systems believes that most of the uptake and most of the revenue is going to come from. And the things in the way of that are the fact that we have to share the infrastructure. So the robot vehicles have to share the roads with extremely unreliable and unpredictable human drivers. And the fact that people just don't have rational risk evaluation methods. We know this from all kinds of spaces, but in the transportation space, for example, a lot of people are afraid of flying, and so they'd rather drive somewhere. Flying per passenger mile is by far the safest way that you can travel, and driving is one of the worst. So they exchange a safe form of travel for an extremely unsafe one because of how they feel. So we're going to see that with driverless vehicles as well. But anyway, that's all this intro material, which I apologize for skipping through so quickly, but we've got some cool extra stuff coming up here in the talk about failure modes, which is really, as hackers, what we care about. So 2 classic failures, one from the aerial space. This is the RQ-3 Darkstar, which was one of Boeing's early expensive surveillance drones for the US military. So it was going to originally cost $10 million per piece, but the prototypes obviously cost a lot more. Here's a DoD video of one of them doing a takeoff run. Unfortunately, not the video I would like to show you. The person who showed it to me refused to give it to me. But on the very first flight, it started that takeoff run just as you saw there, and then started what the journal article on the subject called porpoising oscillations, increasing in amplitude until it flipped over and crashed into the ground and dissolved in a giant ball of fire. However, many tens of millions of dollars on that prototype down the drain. And there's, again, the journal article referring to a nose-high stall and loss of the airframe. So, what happened here? What happened was a lot of the testing of the flight control system had been done on a poured asphalt runway. So without cracks in it. And then when they did this first demonstration flight, it was on a different runway. It was on a runway made out of concrete slabs, and there were small gaps, between the concrete slabs. And as the vehicle was doing its takeoff run, every time it ran over one of those small gaps, that gave a little impulse to the accelerometers in the flight control system. So just kind of a little kick, right? And the flight control system overcompensated for each of those kicks. And by the time it was at speed and getting airborne, it was completely overcompensating and oscillating, and it crashed. So the moral of the story there is the expectations of many of these systems of the designers is critical to the performance of the system and to the failures of the system. And so if we're going to hack or exploit these vehicles, that's probably going to happen at places where different design teams worked on things, or designers had these differences in expectations, these sort of boundary cracks between what was expected when the vehicle was tested, or was designed and tested. Because you cannot test a vehicle like this. It's just impossible to test in all of the kinds of scenarios that they're going to encounter in the real world. So you just have to kind of predict what they're going to see. Here's another favorite failure. This is one of the very early fully unmanned vehicles that was built for the DARPA Grand Challenge in 2004. This vehicle is called Sandstorm. It was Carnegie Mellon University's entry into this competition. For anyone who doesn't remember, this competition was a robot road race from Los Angeles to Las Vegas through the desert. And nothing like this had ever really been done before. It was $1 million prize, and everyone was gung-ho to win this for the first time. Be like, yeah, we were the ones who were out there in the beginning and won. And this one was one of the favorite vehicles for the race because they spent a ton of money on it. They got this Humvee, they covered it in sensors, and it was like, this was the team to beat. You can see it there pulling out at the starting area and confidently driving out onto the road. Well, it got the furthest out of any of the vehicles in this first Grand Challenge. It got about 7 miles, and it ran off the road and caught fire. And that was the best that anyone did. Here's helicopter video of the accident. Total disaster, right? Huge embarrassment for DARPA. So, you know, what happened? The DARPA really wanted this competition to be a success, so they had given extremely detailed route information to the teams the day before. And so this team could have, you know, gone out and walked the course and mapped it down to the meter and just done a complete GPS route following navigation course. But they decided to also, you know, test out all of their sensors and so on, and have the autonomy systems working the way that it was designed to. And so at that curve, they ran into sort of a question of what the robot really trusted. Did it trust this GPS information that they'd plotted out and that had been given to them in advance, or did they trust its sensors? And they made the decision here to trust the GPS coordinates that they'd been given over the sensors of the robot. When they disagreed, they were like, well, we pretty much have been given this GPS information, we're going to trust that. And it turns out at that point in the road, the coordinates weren't quite right. And so even though this was a shallow bend, the robot could totally have negotiated that under normal conditions. It was trusting this other information that it had, and it couldn't make a decision and ran off the road. So deciding what the robot actually knows is a constant battle. Correct state estimation is key to its decision making, and any successful exploits from the hacker perspective is most likely going to subvert its state estimation. So just like with humans, we can think of the logic behind the behavior of an autonomous system as a hierarchical fashion. So at the bottom, we have all our control loops maintaining of a stable platform for the vehicle. On top of that, collision avoidance, because you can't avoid collisions unless you can control yourself. Then you've got navigation and localization, which obviously depends on not getting into collisions, and then your mission task planners and reasoners and so on. So if you can attack anything below, lower in the stack, it defeats everything above. And more engineering effort is often spent on the lower things because it's a requirement. It depends on robustness at the lower levels. So that means lower layers may be juicier targets, but also have a smaller attack surface, much more difficult because they've had more engineering effort. So I illustrated this originally a few years ago with our 2 prototype this examples from the very beginning. The life-saving drone, number 1, aerial vehicle. So it has an autopilot that keeps PID loops tuned for the kinds of conditions it expects to see, the kinds of maximum wind speeds, maximum gust velocities, and so on. No collision avoidance at all, purely GPS navigation. So that means if you can put something in its way, it will totally crash into it. And then the high-level reasoners are just basically setting up this very careful bombing run to deliver its package to the target, which was a self-inflating life vest. So vulnerable to collision, and also vulnerable to attacks on a single sensor, right? If you can mess with the GPS, that platform is completely vulnerable. In the case of the pizza delivery local vehicle, so we've got a 2-wheeled self-balancing platform. So all of its control loops and so on are mostly focused on keeping the vehicle upright. Collision avoidance is done dynamically with a laser sensor. That laser sensor is also used for navigation and localization, building a map and doing SLAM, simultaneous localization and mapping. And then your high-level reasoner is to make sure you only give the pizza to the person who ordered it. So you can see more sophisticated platform in a lot of ways, and more possible attacks depending on what the attacker is interested in. Are you interested in stealing the pizza, or are you interested in stealing the robot, for example? So vulnerable to a whole bunch of different attacks. Last time, once again, I'm skipping through fast to get to the new stuff. Looking at the state machines that are underneath a lot of these systems. So you've got a lot of, some sort of directed graph full of a lot of different states, which may correspond to tasks, and transitions may be task completions, maybe switches in context, may just be simple timeouts where the vehicle decides, well, I've spent enough time here, I either did what I came to do or not, I'm just gonna go back to base. For example, going back home to refuel. And states themselves can also contain like sub-reasoners and sub-planners. So, our vulnerabilities here in terms of logical attacks could be in the state estimation process, could be in preventing or spoofing transitions to make the robot confused about what's going on, or just leading to giving unexpected conditions and unexpected circumstances within those states. So most of the attacks that I'm first going to talk about are going to be looking at the various sensors, how they work, and how we can do bad things to them. So two different types of sensors. We got active sensors where we send out information and get back a return from the environment, and passive sensors where we just passively monitor what's going on in the environment in some way. We have lots of sensors to choose from. And especially ground vehicle manufacturers make use of just about all of them. They really try and throw a lot of sensors at the problem. So GPS, of course, I'm illustrating the locations of these sensors when commonly found using one of Google's early driverless vehicles. So GPS, often 2 receivers on the roof so that you can do differential GPS. LiDAR, which is basically a laser rangefinder. These days, a lot of them use the spinning Velodyne LiDARs there on the top of the roof. Cameras, of course, are cheap and useful. Millimeter wave radar is commonly used as a collision sensor, usually in the front and the back bumpers of the vehicle. Ultrasonic transducers are something that's used primarily for self-parking. Talk a little bit about that later. Digital compass, it's always useful to know what direction you're facing. An IMU stands for an inertial measurement unit, so that's a system of accelerometers and gyroscopes that monitor the movement of the vehicle, and so you can integrate that and see how far you've gone and things like that. Wheel encoders for odometry. And then for other types of vehicles, so not ground vehicles, we have some specialist sensors that you might see. So in the maritime space, for underwater vehicles, a Doppler velocity logger is an acoustic set of transducers that gives you odometry information from the bottom of the ocean or the lake or whatever you're in, and scanning sonar. And then pressure transducers, also commonly used in the air and in the water, so that you know what height or depth that you're at. Sensors give you a best guess at what's going on in the world. You've got sources of uncertainty that are noise, electrical, or your ability to read what's going on, and then drift, which is a change in the sensor value over time, even though the thing that you're measuring is not changing. And then also sometimes takes a while to get a result back from a sensor, latency, and so the real situation may have changed by the time you get this reading. And then also the update rate is important too. So you can model those uncertainties and you make certain assumptions. So if you can make those assumptions not valid, then that's an attack. And then, hey, why don't we just use a bunch of different sensors and fuse that stuff together? That can really help you. Data that's properly registered and fused can be much more useful than separate data. But what do you do, like the sandstorm example, when your sensors disagree? So your robot's robustness may ultimately come down to how good is it at discounting one single sensor that's giving bad information to the system. So here's some types of sensor attack. So you can basically divide your sensor attacks into two types. DOSing the sensor, denial, so basically preventing that sensor from recovering any useful data, or spoofing, so carefully crafting false data that causes that sensor then to retrieve and interpret specifically incorrect data that's been chosen to be incorrect in a specific way by the attacker. And then you can directly, instantaneously attack those sensors, and you can say, all right now I'm going to have the vehicle receive bad information, or you can slowly feed bad information to the vehicle so that it builds up over time a false impression about what's going on. So the main sensor that we love to use above the water, because underwater radio is blocked, is GPS. So GPS is very easy to deny. You can jam it, and that can be just purchasing a $15 GPS jammer from a sketchy website in China. Very easy to do. Or you can get schematics that are available online and you can build your own. Not very complicated systems. That's just basically dumping a bucket of radio frequency noise at the GPS frequencies, and the receiver just can't pick the real signal out of the noise. GPS signals are extremely weak, so very, very easy to jam because they're coming from satellites in space. Spoofing is also possible. You send out carefully crafted fake GPS signals at a higher power than the very weak signals that are coming from space, and you trick the receiver into thinking that's the real thing. So here's an example of doing that for an aerial vehicle. This is from the Radio Navigation Lab at UT Austin. And so they have a animation here showing the helicopter there locked on to a real GPS signal, and the attacker now is creating a fake GPS signal and moving that into place to align with the real one. And then once the vehicle is locked onto the fake one, it moves the fake one off. Because it's at a higher power, the tracker on the vehicle shifts with it. And so then you just, if the vehicle is under GPS control, if you tell it it's drifting up, it will correct and push the helicopter down. And so here's testing on a live vehicle. They're tricking it into thinking in 3 seconds that it's drifting upwards, so the controller takes over and drives the helicopter down to compensate. And if the safety pilot didn't take over, that helicopter is flying straight into the ground. That's how the Iranians claimed that they captured this American reconnaissance drone. They claimed that they sent out a fake GPS signal and caused it to crash. That's almost certainly false in this case, because everyone knows that GPS is easy to spoof, number one, so it's not used as a primary sensor for many military applications. And secondly, there's a military encrypted GPS signal, so that if it was using as a primary sensor, it would use that. More likely, it just made a navigation mistake and crashed. But the claim was that it was spoofed down. And again, military-grade GPS jammers are in use everywhere now. In the civilian realm, GPS often is used as the primary sensor. If you go out and buy a $1,000 DJI drone, it's basically going to use GPS. And in the case of the DARPA Grand Challenge, GPS was used as the primary sensor, as I mentioned. And then resolving the last couple of meters with the laser rangefinder. So here's an example from the second DARPA Grand Challenge, right? So this was, they ran the race again, and this was the vehicle that actually won it. But you can see in this video, there's a straight road. There's nothing to dodge, and it's like going crazy and running off the road. And it's impossible to know without actually looking at the robot's logs, but that to me looks like a classic case of a GPS disagreeing with local sensors. So the GPS is saying, I'm just trying to drag you off to the real path slowly, and the local sensor is saying, no, wait, the road's right here. And so it's just kind of dithering and almost running off the road. Here's another example of pure GPS waypoint navigation gone wrong from the second DARPA Grand Challenge. This vehicle not looking where it's going. It's just trying to follow GPS waypoints, and it goes straight over a Jersey barrier, which I think is awesome, right? Like, who knew that you could drive right over those things? Best done in a rental vehicle, I would say, but you know. So again, the perils of relying on a single sensor. Sometimes a single sensor is all that you have. So out in the ocean, for example, when you're out in the middle of the sea during the day, you've got almost no navigational references. So that same team from UT Austin that did the demo with the helicopter, they thought, wow, why don't we try this with a yacht? It's like many millions of dollars of super yacht. They asked the owner, hey, can we spoof your yacht? And he said, yeah, you mean, the owner was like, you mean someone could like, with a few $1,000s of equipment could come out and like take over my yacht and force it to drive somewhere else? And they're like, yeah. He's like, all right, I want to see that. So they went out there. They did the same kind of stuff as with the helicopter, except in this case, rather than telling it was drifting in a certain direction, like a linear direction, they gave it a spoofed signal that said it was a certain angle off course. So they just pulled it off course by 3 degrees according to the spoofed signal. And sure enough, the navigation system corrected and they were able to drive the yacht significantly off course. 3 degrees doesn't sound like a lot, but when you're traveling thousands of kilometers, you can end up in a very different place at the end than where you intended. And again, there's no reference out there. There's the nav chart showing that they really did it. So that's an interesting result that for, at that time, $2,000 in RF hardware, you can take millions of dollars of yacht off course and potentially cause an accident or use it to do a piracy attack or something like that. So very asymmetrical attack there. GPS spoofing has only gotten simpler over the last few years. So since I gave this presentation the first time at BruCON, we've had a low-cost GPS simulator using Blade RF presented at DEF CON 23. By a Chinese team, and they completely programmed the whole thing in MATLAB, and they demoed it by taking it out to car showrooms and having the car's in-car navigation system think that the car was in the middle of a lake instead of in the showroom. So now, instead of $2,000, it's actually like $300 that you can spoof GPS. Speaking of which, I thought it would be cool, since it's like hard to give a talk about hacking driverless vehicles and do live demos. Can't really drive a vehicle in here and start hacking it. But what we can do is at least do a GPS spoofing demo. So in the interest of time, I'm going to start my equipment here running. We can do this because we're inside, and so our signals will not propagate into the wider world, and we'll transmit at a very, very low power. But I'm going to run my demo here, and you guys use your phone. You'll have to turn off, you have to put the phone in airplane mode so that you're not doing cell tower and Wi-Fi localization, so just pure GPS localization. It's running, and if anyone gets where I'm sending you, yell it out for everyone, and we'll see if it's working. Here's a video of me doing this demo to take over a UAV in a different way. So what I'm doing, I've got a DJI Mavic drone which has built-in no-fly zones. And so what I'm doing is sending out a spoofed GPS location to be at an airport. All the airports in the world are no-fly zones in these drones, and the drone is hovering. As soon as I trick it into thinking that it's at the airport, it auto-lands. So you can take anyone's drone, you can go out to the park when someone's flying a drone, you can broadcast a fake GPS signal at the airport, and the drone will auto-land if the person hasn't hacked their own drone and got rid of the no-fly zones. So here is the video. On the left, this is what the drone operator sees. Suddenly, it gets a location saying it's right next to the runway at an airport, and you'll see in just a few seconds the auto-landing happening. And on the right, that's the view from the drone for me doing this live, and I'm holding up the controller there, and you can see the drone is auto-landing itself. Anyone got a location yet on the phone? I'll do mine too and see if I can see it. Once again, we're transmitting at a very low power here, so even in this room, maybe I'm just going to make sure it didn't crash. That's not where I'm sending you, so you have a... I'll put that up here to get the antenna out of the way of things. Yeah, if Maybe that's wishful thinking on the part of your GPS. No, it's still going. Well, anyway, again, we'll let that run for a little bit. Say again? Correct. Yes, we are all right now in the White House in Washington, D.C., which is also not coincidentally a no-fly zone for drones. So I'll leave that running so that people can see if it shows up on their phones. It sometimes takes a little while to lock because I'm sending out obviously a fake set of, like I used today's GPS ephemeris data. I just generated this file right before the talk. So it shouldn't have to download a lot of ephemeris data if people have used their GPS recently, but if you haven't used it recently, it has to download all the ephemeris data, so it can take a couple of minutes to sync. Anyway, what's going on here? Okay, next sensor. The LiDAR is basically a scanning laser rangefinder. These were originally industrial sensors for warehouses and so on, to show when people went into areas they shouldn't go in because a robot was working or it was dangerous and so on. And then robot people were like, oh, these things are amazing. They're super robust and they're designed to work in all kinds of conditions. Let's bolt these on the outside of vehicles and use them to see things. It uses a laser and a mirror to send out lots of little pulses of light and get a return from all those pulses, and what you end up with at the end is a giant point cloud of 3D points that then is up to you to stitch together into some kind of surfaces and sort of interpret as the world around you. And so these are primarily used for seeing solid objects to avoid collisions and to build maps. So denial of these sensors is pretty easy to do. You can actively overpower them by shining lasers or bright lights at them, or by preventing the object that they're supposed to be scanning from returning a signal, for example, by coating it in an absorbent material. And you can also spoof them by, again, manipulating the absorbance and reflectivity of real objects, or by actively sending spoofing pulses. So here is an example of using it on the pizza delivery vehicle. So we can see here your standard scanning laser rangefinder is a 2D sensor. It sends out basically a horizontal beam of pulses. And so the orientation of the sensor has a lot of dependency there. So for example, inclines can look like obstacles. Whenever this robot leans forward, everything seems to move closer to it because it's pointing the sensor downwards. And you can miss things that are low. So you can drive right into curbs or small obstacles. It's an active emission sensor, so it can only see what returns a signal back. So if it doesn't get a return, it can only assume that nothing's there. And so most of the world returns no data. So think about that. Everything that's over the horizon, up in the air, everything that's too far away, you don't get anything back at all. It's just a blank area in your 3D point cloud. Things that are absorbent, so they don't return anything, also look like nothing, as well as transparent things. So here's two examples of that. If you paint a hole in a wall, just like Wile E. Coyote Roadrunner cartoons, that's made of LiDAR absorbent material, the vehicle just sees that as a big hole and could potentially try and drive through it. And you can also make transparent obstacles that would not be recognized. Another interesting thing about the LiDAR is that things that are reflective can really confuse it, because if there's something at the reflection point that's far away, can be brought to look like they're near. So this tree with the light pulses reflecting off a puddle suddenly looks like it's growing out of the puddle. Similarly, if you don't get a return at all, that just looks like a giant hole in the ground. So if it's big enough, you can make the vehicle think it is a hole in the ground and it'll avoid it. But if it's small enough, the vehicle will ignore it, because this happens so commonly that it's very common to just stitch sparse point clouds together and just ignore the small holes, because there are so many there already, you can't avoid them all. This is an interesting thing that I found, you know, in my browsings of the dark web. This is a document that was captured from an Al-Qaeda offshoot in Mali, and they make reference to certain kinds of exploits and defeats of the systems that are being used against them. So this one is a reference to a military GPS jammer from Russia called the Rakal. And this one is a reference to using reflective materials to deflect laser designators from laser-guided missiles. The reflectance is also used in the civilian space as a feature because sometimes you can infer some things from particular gaps in your return coverage. For example, in road line detection. So optically, detecting lines on the road is notoriously difficult to do, right? Because you know, road markers get dirty when it rains. The reflection of the street lights and stuff makes them hard to see. It's hard to do optically, but it can be quite robust to do it with the LiDAR. So you look for areas that are very precisely shaped where you get no return back because it's reflecting, because the road lines are more reflective than the road. And so you say, okay, that's a line. It's a lane marker, for example. So that means this is the kind of attack that we constantly look for as hackers in this kind of space, is doing things that the robot sees but that humans don't see. So producing confusing output from the system by making things that only the system can interpret and a person wouldn't notice. So this gives us a chance to fake road markings in a way that's visible to the vehicle but invisible to the human, because we can use reflective black paints and so on to paint markings on the road that a person wouldn't see, but the robot sees them really, really clearly. So we can paint swervy lane markers to make the robot do unpredictable things in a street that otherwise looks totally normal. Or then this is just a joke, you know, we could paint markers on the road that the map processors back at the search company see and are amused by. We can also, of course, make objects that are not solid that look solid, because there's very little ability for the LiDAR to determine how solid an object is. Basically, if it reflects back a signal, then it's solid. So we can make a big piece of polystyrene look like a boulder or something like that. And all kinds of other spoofing activities like that. There's been some recent research since I last gave the presentation on active jamming of LiDARs, which is super interesting. So I was really keen to include this. So if you know where the LiDAR is and you can point a strong source at it, then you can prevent it from seeing a return in the area where you are. So here's sending a strong source to overpower the LiDAR. This is research from KAIST last year, and so this is a multi-beam Velodyne LiDAR. So it's instead of just one horizontal beam, it's got a stack of I think 8 in this case. You can get 16 and so on. But so they're getting a definite return here from 3 lines of the LiDAR, and then they're pointing a laser at it, and they're showing that the rest of the return is good, but at the point that they're shooting from, they've overpowered the sensor and it doesn't get a return. So you can appear to be invisible on the LiDAR by sending a strong source. A more interesting result to me from the same paper is that if you use a weaker source, so you're not fully overpowering the sensor, you can actually cause false returns on the LiDAR. And this makes use of the fact that almost all of these 360-degree LiDARs have curved glass around them as for environmental protection. So that's obviously what you'd expect. You wouldn't want to have seams in your 360-degree LiDAR, but having a curved glass means you can exploit the refraction of the curved glass. And so you can modulate the power of your spoofing laser to affect where false returns show up. So this means an attacker, for example, could be driving next to a LiDAR-guided driverless vehicle, could send a modulated signal at its LiDAR and make it think there was an obstacle in front of it, even though the attacker is to the side. And where those results show up depends on the strength of the laser source. So using a weak source, this is super difficult to, I wonder if this has a laser in it. Yeah, this is super difficult to see on the slide. I apologize in the light here. But the attacker is here, the LiDAR is here, and the weak source is showing obstacles in between the attacker and the victim. When that source is somewhat increased, it produces false returns off to the side. So we can, as an attacker, we can craft a very simple attack, just using a laser to simulate obstacles in other areas. And then we can do an even more sophisticated spoofing relay attack on the LiDAR. So this is one where we really need to carefully characterize the LiDAR that we're attacking and set up an active receiver. We've got to listen for its pulses. Use listen, obviously, in the figurative sense because it's not an acoustic sense, but we've got to observe its pulses and send back carefully crafted pulses that anticipate the regular active pulses from the victim LiDAR. So timing is totally critical for where we get to place our fake returns here. And it also takes a little bit of time to characterize the victim LiDAR. But we can see here, here's the attacker, and here's the victim. And the attacker is managing to cause a false return on the other side from itself using one set of timing, and then over here doing the same thing in between. So once again, you're limited to that line described by the attacker and the victim for the most part, but you have some control over where on the line those results appear. Most of the driverless vehicles that are out there heavily rely on LiDAR. It's a really great sensor, good range, good all-weather capability, good large amount of data coming back from it. One exception is Tesla. They, on their autopilot mode, they don't use LiDAR at all. Musk's view is that humans drive basically with vision only and a few additional sensors, so he's really doubled down on mostly cameras. There are also ultrasonics for parking and a millimeter wave radar for collision avoidance. So originally, when I gave this talk, I didn't cover cameras too much because cameras are sort of useful, but for things like specialized object detection, and sometimes you can use stereo for a depth map, although it's super noisy and a LiDAR is better. One of the ways, at the time that I gave this 4 years ago, one of the main ways that cameras were used, because they were mostly unreliable in other ways, was to what's called colorize the LiDAR. So that's where you take your 3D point cloud and then you give a color to it based on fusing that with your vision data. And that lets you do things like say, okay, the road, which my LiDAR says is drivable, is mostly this color. So then I'm going to extend my color detection out beyond the LiDAR range and say, okay, all of that stuff ahead is the road, and we can just drive really fast. So this is how Stanley, the Stanford vehicle, won the second DARPA Grand Challenge. After the first one was a total disaster, no one got more than 7 miles. The second one, a year later, several robots finished, and this one finished in quite a good time because it just drove really fast using mostly this technique of deciding what a road looked like on the LiDAR and then what color it was and driving fast. So cameras are easily dazzled. They're spoofed by camouflage techniques and by certain assumptions they might make about color, and by repeating patterns in the case of stereo. One thing I wanted to include this time around, since it's, looking at this later on, was the recent research that's been done in adversarial trickery of deep learning models. So this is all the rage right now, is building a deep learning system to recognize whatever. So for example, a stop sign, you can do this totally feature-based and say, I'm looking for red octagons, it works really well, or you can train up a neural network to do it. If you train up a neural network to do it, it turns out you can fool that neural network pretty easily with some pieces of black and white tape. Any human is still going to see this as a stop sign, but the robot doesn't. Then there's some stuff that's been done where they do deep learning models, for example, pedestrian detection, and then, again, it's totally impossible to see on the slide, but by crafting a certain amount of adversarial noise and adding it to the image, you can make the robot say, oh, those pedestrians aren't there at all, completely fails to recognize it. Of course, this is not really a practical attack, because if you have the ability to inject carefully crafted adversarial noise into the image that the vehicle is seeing, you obviously have access to the insides of the robot, and there's lots of other ways you can mess with it. So not super practical. And these things are also generally white box techniques. So the people who are designing the adversarial attacks are also designing the neural networks. They know exactly how they work, and so they know how to craft examples to fool them. One interesting, these are also not particularly robust in general, although an interesting paper that came out just recently was one where they were able to 3D print models. They trained up a neural network to recognize certain objects, and they could 3D print models that were that would fool the recognition engine from multiple angles. So the system, in this case, this adversarial turtle, the system thinks it's a rifle from a variety of angles from this 3D printed model. The millimeter wave radar is a sensor that Tesla's using in the autopilot, Google's using, or Waymo now on their vehicles. This is the stuff that lets the airport security people see your junk at the airport. Primarily used for collision avoidance, and it's a much lower resolution than the LiDAR. So it just kind of tells you there's a big fat blob ahead of you and don't run into it. Many things basically look like a mirror to the millimeter wave radar. And so you can jam it, just like with the LiDAR. You can use anti-radar techniques that are common in the military, like chaff, and just things like overhead signs, things that are extremely reflective. The radar is not really able to discriminate. So if you were just relying on the radar and there was someone parked underneath a big overhead highway sign, your car would probably run into it. Here's an example from Tesla's autopilot. This is the Bosch LRR3. And hacks, since I gave this talk at BruCON before, hacks of these have been presented. So at DEF CON 24, another Chinese team looked at jamming this radar. So this is from a Tesla autopilot, and you can see here there really is something in front of it, but when it's jammed, it looks like there's nothing in front of there, so you could make the vehicle run into something. They also theorized spoofing and relay attacks, but didn't perform them. This equipment here, it's not like the GPS spoofing. It's about $100,000 worth of equipment, so this is an expensive attack. The IMU and the compass, we talked about earlier, the accelerometers and gyros. So this is the primary navigation system for certain systems, like military systems, or like underwater oceanographic systems that don't have access to GPS. So you can get really high fidelity models. So like if you get an IMU from a Boeing 777, for example, has about a 0.1% of distance traveled error. So if you go 300 kilometers, at the end you're within 300 meters from where you think you are. That's pretty good. These are very difficult to interfere with because they're completely passive and on board. But they are susceptible to magnetic fields and to thermal drift. So if you're able to get close enough, have physical access to the system, then you can mess with them. And that distance is pretty small for magnetic and thermal attacks. But again, since I gave this talk before, people came up with a really interesting acoustic attack against IMUs. So acoustics, again, your standoff distance is not great. But it turns out, in the case of MEMS gyros, so this is micro electrical mechanical systems that you would find low-cost drones like any of the commodity Chinese aerial drones and so on. they have these MEMS gyros in them, and the MEMS gyros work by vibrating a small mass and then measuring the perturbance of that mass when the system rotates. So it turns out if you can hit those things with a frequency that's close to the resonant frequency of the mass in the MEMS gyro, you can basically make it go crazy and not be able to record any data at all. So this was POC'd by a group at KAIST in 2015, and you can see here when they turn their acoustic blaster on, the controller of that quadcopter on all 4 rotors goes completely nuts, and they were able to crash the quadrotor basically by beaming a sound out. It's basically a variant of the screaming in the data center attack that's been in vogue again recently because people suddenly rediscovered the fact that you can play loud noise at hard disks and vibrate, spinning hard disks and vibrate their read heads and cause them to fail. So same kind of thing. So you could make a very localized UAV point defense system with one of these systems if you could generate a high enough sound pressure at whatever distance you can do that at. So probably not more than 20 or 30 meters or something like that. Wheel odometry, just very quickly, since I know I'm running out of time here. Very useful to know your real speed, and this is actually what caused a failure for us doing our pizza delivery. We successfully crossed the bridge, but as it took this turn a little close, this is a very difficult turn that human drivers crash into that wall all the time, as you can see from all the scrapes, and the vehicle knocked its wheel encoder off and then was just very confused. It was like, it says I'm moving forward, I think I'm moving forward, but my encoder says I'm not, and it just didn't know how to respond. So that's a super easy attack. And there are other ways too, like changing the wheel diameter if you have physical access, where you can attack that particular sensor. I originally didn't cover ultrasonic sensors when I last gave this presentation, but now attacks have been presented on them, so I felt for completeness I should. They're only really used for parking, so they're only used at low speeds, so who cares really, but anyway, there are a bunch of attacks that were shown at DEF CON, so I'm including them. So with a Tesla and an Audi parking sensor showing that jamming is possible by sending out just acoustic ultrasonic noise. And then you can also spoof it too by sending carefully timed chirps to make it think that things are there when they aren't really. You could also do a cancellation attack because it relies on these acoustic waves, but that's a kind of a reverse spoof to make it think that something's not there when it really is. So originally, 4 years ago, I had James Bond versus the robots. So the Bond vehicle to attack driverless vehicles would have a GPS jammer, have smoke and dust and vapor ejectors to confuse LiDARs. We'll have lightweight decoy obstacles that the robot vehicle couldn't ignore, chaff for the radar, and glass caltrops against the tires that the LiDAR couldn't see, and of course the oil slick to interfere with the wheel odometry. And now our new Daniel Craig James Bond vehicle 4 years later now contains an active LiDAR jammer and spoofer, an active radar jammer, an acoustic blaster to deal with the MEMS gyros, and an adversarial turtle dispenser. So I'm actually, not all the way at the end of this, but I know that I'm hitting my end of time. So I'm just going to quickly skip ahead and just point some things out about the map, because the map is something that all of the driverless vehicle systems out there are really heavily relying on now, right? That's something that they say, well, driverless vehicles is hard, but we're already mapping the world in a very detailed fashion, so we'll make our life easy by really depending on this high-fidelity map that we create. And so one place that they do that is with traffic lights. It's hard to just look around you and know, if you're a robot, what's a traffic light and what isn't. But if you know exactly where the traffic lights are, and you know exactly where to look, then you can just detect the state of the traffic light. So you don't have to do traffic light detection, you just have to do state recognition. So you just have a little camera that looks every time you know where to look for a traffic light, and you say, is it red, yellow, green? what that means, again, is we have a difference that we can exploit in robot versus human assumptions. So if we have a fake traffic light, humans are going to stop for it if it says stop. Humans are going to go through it if it says go. If the robot doesn't know it's there, it's just going to ignore it, and so we can perhaps cause it to crash by telling the human to go when the robot is coming the other way. Vegetation is something that we can easily confuse the LiDAR with, because the LiDAR will often be used in a colorized fashion to say, oh, this stuff like looks solid, but it's green, so I can drive through it. It's just a bush, but they can make something green that's not a bush. And we can also confuse it with things that are overhanging that a human would ignore, but the robot says, oh, here's this like, and I've seen this happen in reality, riding in these vehicles, that the trees have grown a little bit since the map was created, and now the robot's like, oh, no way, I can't go through there. And you're just like, come on, dude, it's just some leaves on the tree. We can also, if we rely on a map on our driverless vehicle, now, well, is the map on board, in which case we can put unexpected features in the real world, or is the map coming from somewhere remote, like it is when we use our phones, in which case we can deny the map, so we've got just the same as a sensor attack. We can jam it, or we can spoof it by doing a man-in-the-middle attack and giving false map information. Basically, our goal here is to concentrate on fragile maneuvers if we want to mess up the robot, and craft our attack to take place at a place of maximum uncertainty to the robot, and hopefully cause it, for example, to have a crash. And if we're doing physical attacks, we have the ability as the attacker to craft quite sophisticated devices that also contain sensors and knowledge about the real world. So we can do our physical attacks, for example, with a device that also has a GPS in it, and choose the place to do those physical attacks, to overwhelm the gyros, or to do a magnetic attack, for example, on an IMU. There's an example of that just came out too, where a group used a GPS spoofer with its own GPS that would carefully send out spoofed GPS signals that would cause a navigation system in a car to give completely false directions to a human-driven vehicle. So the person would turn left when it was told to, turn right when it was told to, but actually would be directed to a completely different place. And then these slides are just about different ways that we can, different outcomes. We might want to trap the robot or redirect it somewhere. We might want to cause it to crash into something. Finally, we don't want to actually do any of these things. Don't hassle the Hoff 9000, or don't hacker the bots. We're just doing this, obviously, as researchers to try and figure out ways to make these systems better. One more thing right at the end that I gave last time, which I don't really have time to cover now, but this stuff is not new. It's been out since I think 2014. So this is kind of a joke from Technology Review, talking about how bad things really were in 2014, and the fact that we might not actually see robots on the road all that soon, because it would just drive straight over a big hole. At that time, also, the Department of Transportation in the United States came out with this plan for vehicle-to-vehicle and vehicle-to-infrastructure communication. So originally here I covered, this was new, and so I covered sort of how this worked and what its potential vulnerabilities were, which I won't do in great detail now due to time. But the point was that this was something that was being rolled out right now, slowly, that we're going to start to see these messages be transmitted between vehicles, that obviously hackers could send false messages or jam them and so on. Right now, they're just warning messages. So they're things like lane change warnings or collision warnings. This is unencrypted basic safety message, so we can generate them, we can read other people's ones, but they are authenticated with signatures, but with certificates rather, so we all know about the problems with PKI and certificates. So here's some stuff that describe this rollout, and the extremely limited initial rollout and the timeline. So most of the management functions like that are split are for privacy protection. So a lot of the emphasis here is on privacy of the vehicle driver, not really on security of the overall system, although obviously that's important too. But basically the upshot is it's going to be super easy to get valid certificates, and even though they only last for 5 minutes for privacy reasons and so on, that's a long time on the road. Took 11 years to be developed, 37 years to be rolled out to the full fleet, and so far tracking and privacy has been more of a concern than malicious attacks. And again, it's only warnings for now, so it's actually possible that robots might be out there before this system is taking active control of your vehicle. But one update to that since 4 years ago was just comparing with some of the traffic sensors that are out there. One of the researchers from IOActive gave a presentation at DEF CON 22 on just all the problems with traffic sensors and with the way that we hope that V2V and V2I will avoid these total rookie mistakes. So these sensors are just all over the place. They're buried in the road. They're impossible to or like prohibitively expensive to dig up and replace and fix. So they have no encryption at all on their transmissions, no authentication, clear text wireless transmission, everything that we have been laughing at for years. Firmware updates, because they're buried in the road, they have to be wirelessly updated, and so their firmware updates are neither encrypted nor signed. So just a total shit show. Again, for V2V and V2I, we hope to avoid those mistakes, but no doubt others will be made. So that will be a fruitful area, I think, for car hacking people to look at in the coming years. So that's it. I'm sorry for racing through the stuff so quickly because I added all this extra stuff, but hopefully that gave you a flavor of what this was like as a retro talk 4 years ago when we were just getting excited about driverless vehicles, and then the pretty cool new research that's happened in the last few years. And once again, I like to misappropriate propaganda posters. So this is the pro driverless vehicle propaganda poster of living the dream of the car driving itself while we get down to business in the backseat. Thanks for your attention. I know it's lunch now, so I guess people can, I won't feel offended if people just go to lunch, but if people want to stick around and ask questions, that's cool with me. Thanks.